Hi, my name is Georgi Radulov, and this question here asks us about what are the poles of the common mode rejection ratio for this circuit. And this circuit is the standard differential pair that is implemented with a tail current which has certain output impedance, capacitance and resistance. So the question also gives us the dominant pole for differential gain, which is at 500 kilohertz. Let's start with this question. First of all, what is common mode rejection ratio? So common mode rejection ratio is a figure which gives the ability of a circuit, given circuit, in this case the differential pair, to amplify differential signals and suppress common mode signals. So what are differential signals? Now, this circuit is meant to operate with differential signals, hence the name differential pair. So differential signals are two signals with change in the opposite phase. So if this signal goes up, the other will always go down. And then the signal, actually the input signal, for example, signal V in, will be always defined as their difference. So V in plus minus V in minus. So say this is V in plus and then this is V in minus. Right? So here, for example, we can imagine one of the signals, sine wave, and this is the other signal. Always the opposite. So for example, if this is, say, V in plus, this is V in minus, and the signal V in will be always the difference. This is how we define the differential signal. So how does this circuit works? If for example this signal increases, it increases here the VGS. If there is a larger VGS, there will be somewhat more current flowing here, which will be defined, of course, by the GM of this transistor and the change of the VGS. And because this VGS here became a little bit smaller, then this current will decrease. I can just draw it with the opposite direction of the current. So here, because we have more current flowing, there will be more voltage drop across this resistor, and then this voltage will have to go down. So we can name this V out N. And then the opposite about the other branch. This current, since it decreases, the voltage drop across the load here will reduce, and then this voltage will actually go up because the voltage drop across the load resistor is small. And then we will define the output as the difference between these two, so differential output. Now let's see what is the power, what is the good thing, the big advantage of differential signals. So we will have to of course consider that these wires, they come to somewhere, they propagate, and imagine that there is a disturbance on the way. So a circuit, for example, switches, and then these signals that switch are coupled to the wire. So this introduces some disturbance in the wires that bring the signal V in. Now, if these two signals go together like this, so they propagate, and here we have a disturbance, the important thing that there will be is that this disturbance is common mode. It will be the same for both wires. So say that it happens somewhere here, and there is this disturbance. So for a certain period of time, the voltage decreases rapidly. Because the effect will be the same for both signals, I expect also that this will be disturbed. So we have here an error, and we have the same error here for the other signal. So now, because we always consider differential signals, we will subtract them, and then these errors will actually cancel. Now, the error is common, hence the common mode signal variation, while the signaling that we use is differential. So for common mode signals, then this differential pair here, this circuit, operates differently. Imagine that this goes down, this signal here. Then for common mode signals, per definition, this also goes down, right? So now this node will have to also decrease, because now this decreases, this node is in between, and it decreases by the same amount. So if we have change in certain voltage in certain node, then we require some charging or discharging of this capacitance. If there is charging or discharging of a capacitance of a node, this means that there will be a time constant, because these charges should come somehow, and they come and go out through a time constant. This means that this will create a pole. Yeah. So in the common mode rejection ratio, then we have, of course, the contribution of the differential poles, but we also have contributions in the frequency dependence of the common mode rejection ratio function of the poles of the common mode gain. So this brings me to the question: what is formally the common mode rejection ratio? Intuitively, we discussed that this is shows the ability of a circuit to amplify differential signals and to suppress common mode signals. Formally, it is defined as the ratio of the circuit differential gain and of the circuit common mode gain. So here I can write the common mode rejection ratio is a ratio between the gain for differential mode of the circuit, so for differential mode, dm, and the gain for common mode. We already have one pole for the differential mode gain, so it will be here, and we need to find the poles of the common mode rejection ratio, so we have to analyze then the frequency behavior of the common mode gain. We have a feeling here of what will happen as the frequency go higher, so basically as this disturbance becomes higher and higher frequency, then the impedance that we have at this node will basically decrease. So the common mode will effectively increase, because from a common this transistor operating in a configuration of at low frequency common source amplifier with degenerated gain that is very high, so this is 1 mega ohm, it will go to almost ground at very high frequencies. So the common mode will increase, and we want to investigate this. Let's see what is the gain for differential signals. So the problem gives us that one of the poles is given. So then the differential gain, if there is only one pole, in most cases can be considered as certain DC gain, which will be, like A0 will be something like minus GMR. So I'll write it here. So A0 will be something like minus GMRD. Yeah. And then there is one pole. So if there is one pole behavior is as t as tau, where tau is of course 1 over omega b, yeah, and this is the corner frequency, and s we substitute with j omega. So for the differential gain, then we can have the DC gain divided by 1 plus j omega divided by omega b, the corner frequency, and of course omega is 2πf, because this is given in hertz. So then for the differential gain we get 1 plus jf divided by fb. All right, so this will be then the pole that we have. Differential signals, of course, the circuit operates like this. So if this goes up, this goes down, and it's very important now to realize that this node is in between, as this input change up, this change down by the same amount, and this node is between a symmetrical circuit. So then this means that this node will not change. If this node does not change, this means that for differential signals, this will be a small signal ground. It will never change for differential signals. As for example, this goes down by exactly the same amount, this will go up. Again, this node here is in between and it will not change. If this is a small signal ground for differential signals, then here these capacitances and resistances will not matter, because they will be connected between ground and ground. So that is to say that for differential signals there will be no poles or zero coming from the output impedance of the tail current source. Of course, for common mode signals, the circuit operates differently. Now imagine this goes up, and then this goes up also by exactly the same amount. This node here is in between, and this will go up also. So then we have charging and discharging of this part, and then we have to see what the effect of pulse and zero will have, what the effect of this time constant here associated with this node will be actually. For very low frequencies, we can say that we can ignore the capacitance, for example, for extremely low frequency, and then the impedance will be dominated by 1 megaohm. Well, this is something very big, and this will be like almost like floating this node. Now, if this node floats, actually the gain that we will have of a circuit which is, you know, like this, if you can imagine, for common mode signals. Yeah, this will be just floating. This gain will be zero, so the common-mode rejection ratio will be very large. Now, as we go to high frequencies, the capacitor will behave like short circuit. So we'll go from this circuit for low frequencies, so this is for low F. We'll go to this circuit for high frequencies, right? Because this at high frequency will act like short circuit. Now this is common source amplifier, and it has a lot of gain, so it will be GMRD. And then for the gain in common mode, we'll get from very small to very high, which will basically degrade the common mode rejection ratio. And exactly this, so the pole of the common mode rejection ratio, is what we want to find. So how to approach this circuit? We know that it is fully symmetrical. You see here that this circuit is symmetrical, what is in this side is exactly the same as this side. We have for common mode signals that this changes in the same way as this changes. And then here, the common part can be split simply by 2. And then we'll have a circuit of this type, which we can easily analyze. So this is done in next slide. So here, what we see here is how we split the circuit in 2. So we have to split the current source. So for the 2 halves, we have here 1/2 of the tail current. We have to split the capacitance. So we will have from 10 picofarads, we will have 5 picofarads, and we have to split the resistance 1 mega ohm in 2, and 1 mega ohm is like 2 resistors of 2 mega ohms in parallel. So this circuit here is absolutely equivalent with this circuit. They are the same circuits. And because the input signals that we analyze are for common mode, this means that they change in the same way, which means that if we analyze only half of the circuit, will be absolutely enough, because the other half behaves exactly in the same way. So now what we have is for 1/2 is shown here basically, and this is circuit which we call source degeneration, common source with source degeneration, in the sense of this here for small signal acts as a negative feedback. If this is extremely large, so floating, then the gain will be, of course, 0. And if this is ground, so basically shorted through this capacitance for small signals to ground, then the gain will be very high, Gm of this transistor times Rd. So let's analyze this. To analyze this, we need to go from the large signal schematic, which is given here, to a small signal equivalent model, with which we can apply linear analysis and find an exact expression about the common mode gain and its frequency behavior. So we start with the most important component, substituting the most important component, which is the transistor. So the MOSFET, its main functionality is given by a voltage dependent current source. So this will be the node drain, so it's drain here, which is V out. This node will be V out, and this will be this node Vs, its source. And of course the value, the current in this voltage dependent current source will be given by the Gm of the transistor, and then the voltage gate source voltage. And for the gate we have V in common mode, the input signal at common mode, V gate minus V source, which is Vs. Yeah, so again, this is Gm, simple Gm VGS of this transistor. Now we have this node, which is actually this node. Here we have the resistor Rd, which is connected to the VDD. Alright? But VDD for small signal is small signal ground. Why is that? Because VDD is simply a voltage source that is connected to ground and provides, of course, the power supply. And as we know, for small signals, we substitute the independent voltage sources, for example, like the VDD, with short circuit. So we will just connect it. Hence, this VDD becomes small signal, for small signal ground. Then we are here at Vs, so this is this point. The current sources are left open circuit, so we just do not include them in the small signal equivalent circuit. So this is independent of the input signal, so we will ignore it. And then we have, of course, the capacitance to ground, which can be modeled with its impedance ZC 1 over SC, and we have the resistance like 2 mega ohm. So this is now here, this is the equivalent small signal circuit of this transistor level circuit. Now, this is a simplified version. The effects that I ignore at the moment are the channel length modulation of the transistor, or R out. If I want to include it, I have to put it like this in parallel. R out of the transistor in parallel with the GM current source. This is the channel length modulation, and I ignore it because this will complicate my calculations while will not add to the accuracy of the solution. The other thing that I ignore is the body effect. Yeah, so this has to do with the fact that here it's not shown, but the bulk is usually connected to ground. And now I have a voltage between the bulk, here the bulk of the transistor, and its source. And as you know, the bulk acts as a second gate and influences the threshold voltage of the transistor. So if we have to include this will be like a parallel voltage dependent current source with a value of a coefficient GMB, which models the body effect, and then the voltage V bulk source. Again, this will complicate very much my analysis, while it will not add accuracy in my analysis. So I will ignore it. This is the equivalent circuit, and I can combine the capacitance with an impedance 1 over SC. I can combine it with the parallel resistance in a common impedance ZS, which will be the 2 mega ohms in parallel with 1 over j omega of 5 picofarad, or I can treat this as the admittance 1 over the impedance, and then I'll just sum the admittances of both. So 1 over 1 divided by 2 times Rs plus 1/2 of j omega Cs. Now I want to find the gain from this circuit, and this will be my common mode gain. So all I need to do is to write the Kirchhoff current law. So basically I need to solve this circuit. Yeah. Small signal equivalent. And the approach will be to write the Kirchhoff current law for this node here. So perhaps I can also draw for this node, and then for this node also. So I'll have two equations, and then I will eliminate one of the variables that I don't need, Vs. So I'll have one equation which will link the output voltage with the input voltage, and this is how I'll find the common mode gain, which is of course defined as the ratio between the output and the input. And I write here common mode because I explicitly analyze the circuit for common mode signals. So let's start with this. First we write the Kirchhoff current law for node V out, so KCL at node V out. Looking at V out, KCL is easy. We have this current plus this current. The sum is 0. So this current here is simply V out divided by RD, and then plus this current, which is of course GM of V in common mode minus Vs, here this, and the sum is equal to, the sum of this is equal to 0. Alright, so from here I can work it out further, that so I can open these brackets, and then I have V out divided by RD is equal to GM, no, not equal, plus, sorry, GM times V in common mode, and then equal to GM Vs. Yeah, and from here I can express Vs to be, so I'll divide by GM, and here also, like this. Now I have an expression for Vs, which is of course that Vs is equal to V in common mode, so I can write it, V in common mode, and then plus V out divided by GMRD. Now at this point, if you want to take shortcuts, you can say that this is just a source follower. So the V source here, this voltage is almost following the input voltage, and you can ignore this. If you want to be more accurate, you can keep it. So it's a question of accuracy of the analysis. So if we want to eliminate Vs, we can consider here Kirchhoff current law at this node. So now KCL, Kirchhoff current law at node Vs, then this will be this current, which is GM of V in common mode minus Vs, is of course equal, so this current is equal to the current that goes through this impedance, so basically this current, which is of course Vs, and then if I take this as a co, this will be Zs, where Zs is here, this thing here. So from here I can eliminate the Vs signal. So now we have to combine both equations. So we can take this thing here, like this, and just plug it here. See? Yeah? So this is just plugged in here, which basically says that I can write now that V out, so this thing, is equal to this, yeah, with the opposite sign, of course. So just let me write it. V out divided by RD is equal to minus Vs Zs. So here now, from this equation, I still have Vs, and I can eliminate it taking this equation here. I have here an expression for Vs, and I have to plug it in here. So I can write it somewhere here. So I have V out, so minus V out divided by RD, which is this thing here. And now I have on the other side, so this is equal to this Vs, but for this Vs I'll write this part here, which will be V out divided by GMRD, and then plus V in common mode, so this thing here, and then divided by this ZS, like this, and I'm almost done. So let me clean a little bit. Now I can write V out RD multiplied by ZS, and then minus V out GMRD is equal to V in common mode, like this. Now on the one side I have V out, you see, so I can take this thing here. This will be V out multiplied by this equal to V in. So from here I can directly write what will be the gain. So the common mode gain will be V out divided by V in common mode, and this I will work it out more. So basically this here will go down, and then I'll have something like 1, and I'll write it here 1, and this will be 1 divided by GMRD here, and then plus ZS divided by RD, like this. So now here we recognize that this part here, let me take another color. So we recognize now that this part 1 over GM is much smaller than ZS over RD. You see here GM is usually large and it multiplies RD. Well, here we have ZS, which means that this will be negligible. And then I can simplify this to simply RD ZS, or RD, so this is RD. This is the admittance. Yeah, this is YS. Alright, so now I have an expression about the common mode gain.
Can be calculated with the number that we have to be 10 to the power of minus 6. So I'll just rewrite it here. So the common mode as calculated was minus RD divided by ZS, and for
ZS is this here, so as given here. If you work it out, you'll have in the common mode a 0 here, this, and the 0 of course is 1 over tau s, where tau s, the time constant of ZS, of here of this capacitor and resistor, is Rs times Cs. You can calculate what it is, and then in hertz, in kilohertz, this will be, so in hertz it will be 1 divided by 2 pi of this. If you plug in the numbers, you should get 15.9 kilohertz. So then for the common mode rejection ratio, we get, of course, we were asked for the poles, and then there will be certain common mode rejection ratio for DC, and then times the frequency behavior of it. So we will have one pole which is given because of the differential signal, which is one pole is just 500 kilohertz. So F then divided by 500 then kilohertz. And then I will have, of course, another pole, which is due to the zero in the differential. Gain. So you remember the common mode rejection ratio was the differential gain divided by the common mode gain. And this common mode gain will be will have frequency dependence. There will be a zero, and the zero for the common mode gain is like a pole for the common mode rejection ratio. So the zero will come here, which we calculated. 9 kilohertz. This is what we calculate. Now, so if we look at the common mode rejection ratio in the frequency domain, you will start with a very high level. So the circuit at very low frequency will be very good in amplifying differential signals and suppressing common mode signals. However, there will be one pole, which is the pole for the differential gain. So at certain point, the differential gain will decrease. This will also cause the decrease in the common mode rejection ratio. Then at low frequency, the gain for common mode signals will be very small. So common mode signals will be suppressed. However, because there is a zero in the transfer of the common mode signals given by the output impedance of the tail current source, this zero will mean that the gain for common mode signals will increase after the zero by plus 20 dB per decay, which means that in the denominator of the common mode rejection ratio, the transfer will increase and the common mode rejection ratio will decrease. So this zero for the common mode gain will be like a pole for the common mode rejection ratio. So thank you very much for your attention. Bye.